Here's a short justification for the definition of conditional probability. In the week 3 online video lecture, there was an intuitive motivation for the definition of conditional probability, and that was done using two-way tables. So if we knew that a certain event was given, we would restrict our attention, in essence, shrink the sample space to just those sample points that corresponded to event B occurring, and then we would figure out of those sample points what proportion of them corresponded to event A also occurring. And what that yielded us was this probability of A given B is equal to the probability of A intersect B divided by the probability of B. So here let's take a little bit more mathematical approach to coming up with this equation. And just like with the assumption of equally likely outcomes, I want to show you that this formula is the only formula that makes sense if you follow the rules of probability, as we stated previously, and make a couple of assumptions on top of them. Now, most notably here, we're not going to make an assumption of equally likely outcomes. All right? But there are two assumptions we need to make. So here on the left is the sample space S, and I have a bunch of sample points, S1, S2, then up to SK plus 1, K plus 2, K plus 3, K plus 4, all the way up to N, right? So there's N total sample points. Some are in A, some are in B, some are in both. And so what we're going to do is make two assumptions. First, for any sample point not in B, so is not an element of a set. So every sample point that's not an element of B, I'm going to assign a conditional probability for the simple event containing that sample point. Right? This is the curly braces, a single sample point. This is a simple event, but it's conditioned on B. Right? I'm going to define that conditional probability to be 0. In other words, if I'm told B occurs, then every sample point that doesn't correspond to event B occurring, I'm going to give it a conditional probability of 0. This is, in essence, my way of restricting my attention to a subset of the sample space. In a two-way table, I would restrict myself to either one column or one row. Here I assign a conditional probability of 0. Now, for sample points, S sub I, that are in sample B, or in set B, I assign the conditional probability of the simple event containing that sample point to be proportional, a constant times the unconditioned probability. Now, I don't know what C is. I'll have to determine that. The reason I define or I make this assumption is that if one sample point was twice as likely to be observed as another in the unconditioned probabilities, then after I move to conditional probabilities, I would still like that one sample point to be twice as likely to occur as the other. So this keeps the relative sizes of probabilities the same from before the conditioning to after the conditioning, at least for those sample points that are in event B. For all the other ones, they just assigned a value of 0. So now we go back to the rules of probability. The probability of the sample space itself is going to be equal to 1. Right? That's everything. So now what I do is I write that it's the sum now of all the probabilities of simple events, but I'm not adding up the regular probabilities. I'm adding up their conditioned probabilities. Right? So this sum still has to be equal to the probability of S, which is going to be 1. Now what I'm going to do is I'm going to break this sum up. This is over all sample points from I equals 1 to little n. Remember that those subscripts are my sample point notations up here. And I'm going to break it up into first a sum from I equals 1 to k. So that's these sample points up here that don't belong in event B, plus a sum from I equals k plus 1 to n. So that's all the remaining sample points over here. Now, because all the sample points in this first sum are not in B, by my first assumption up here, all those conditional probabilities are 0. So this whole sum on the left here is just equal to 0. And then the sum on the right here from I equals k plus 1 to n, these conditional probabilities all become that unknown constant C times the unconditioned probabilities. So that's what I get at this line down here. And now because I'm summing up a bunch of numbers and each one is multiplied by c, I can factor out that common multiple of c outside the summation there. And so what I have left here is a sum from I equals k plus 1 to n of the probability of all the simple events, and all those simple events have sample points that fall in event B. So by definition, this sum here is simply the unconditioned probability of event B. So I get C times the probability of B, and because this whole thing was originally equal to the probability of the sample space, I have C times the probability of B is equal to 1. So then I can divide through and solve for C being equal to 1 over the probability of the given event. So now I know what that scaling multiplier needs to be up here in assumption 2. Now, finally, to figure out what the probability of event A given B should be, I will sum up here all these simple event conditioned probabilities from I equals 1 to k plus 3. So these are all the sample points that fall in event A up here, all the way up to k plus 3. Now the first k of them are only in event A, they're not in event B. So all those conditioned simple event probabilities all go to 0, so this whole term drops to 0. And I'm left simply with the sum from I equals k plus 1 to k plus 3 of those conditioned simple events that are both in event A and event B. Well, from assumption 2 earlier, all of those guys, since they're in B, are a scalar times the unconditioned probabilities. And I now know what that scalar is. It's 1 over probability of B. So I plug that in right here. Now 1 over probability of B, that's just a number. It's multiplying everything I'm summing together. So I pull that outside front there. So I have 1 over probability of B. And what I have left here is a sum of probability of simple events. And all those simple events simply correspond to sk plus 1, sk plus 2, sk plus 3, meaning they are the simple events that when combined together give you the intersection of events A and B. So that's why at the very end here I get the probability of A intersect B, or A and B, over the probability of B. And that is the definition that was provided for conditional probability. So just like the classical approach to probabilities formula, where you count up the number of sample points in the event you're observing, divided by the total number of sample points possible, this formula also is simply a result of rules plus assumptions, and we get this one and only one formula for conditional probability.